Here we examine the effect of a long straight wire called the primary, that'll be this here, carrying some time-dependent current, I1 as a function of time, on a nearby loop of wire, this rectangular loop here, which we'll call the secondary. So there's no power source in our secondary loop here, it's just a piece of wire sitting there. But there is a battery or power source somewhere that's driving this current in our primary wire, and that is adjustable to be time dependent. So let's first consider Lenz's law and see if we can predict the effect of electromagnetic inertia on such a system. So two examples here. I'll talk through this one, then I'll have you predict what will happen in this one. So suppose first that this current I1, the primary current, is increasing with time, so getting stronger with time to the right. What effect is that going to have on our secondary loop? First, consider that this primary current is going to be generating a magnetic field in the region around it. So grab onto that wire with your thumb pointing in the direction of the current and your fingers curl in the direction of the magnetic field that is looping around this wire. So we see that our B field will be coming out of the page, up above the wire, and then into the page, down here below the wire. So let's show that B field up above and down below. That'll be B1, which will be a function of time since it's being generated by this current that is a function of time. Okay, well, if this current is increasing with time, that means our B field that the primary is creating is getting stronger with time. So over time, we're getting an increasing magnetic flux through our secondary loop right here. So we have a flux coming out of the page, and that's getting stronger with time. This system will respond by trying to oppose that changing flux. So since we're adding flux out of the page by increasing the current here, this system will respond by trying to add flux into the page. And the only way that'll happen is if a secondary current starts running clockwise in this secondary loop. Use blue for that. I2, which could potentially be a function of time as well, running clockwise in the secondary loop, will be putting its own magnetic field into that loop to oppose the changing flux. Okay, so there's Lenz's law predicting that we would get a clockwise induced current. That's I2. Our secondary current is the induced current in the secondary loop. Okay, now you predict what's going to happen in this case. This time, the current in the primary wire is going to the left, and suppose it's decreasing with time. So it's going to the left, but getting weaker with time. Pause the video and run through the same set of logical steps as we just went through here to predict what kind of secondary current we're going to get in this loop. You got it? Figured out? Okay, here's what's going to happen. This current here is going to be generating a magnetic field into the page up above and out of the page down below. So here is the magnetic field being produced by our primary. So the primary magnetic field here. So that's creating a magnetic flux into the page through our loop. But if this current is decreasing with time, that means this flux into the page is getting weaker with time. The system will try to respond by attempting to replace the flux into the page by supplementing the flux into the page that we're losing as this B field weakens. So the only way that this loop can generate more flux into the page is if we get a clockwise current running through that loop there, generate flux into the page. So it happens to be the same outcome as here since we flipped multiple things. We flipped the direction of the primary current and we changed it to decreasing instead of increasing. Those two flips ended up with us getting a clockwise current in this secondary as well. Okay, so that's conceptually, qualitatively what's going on. Now I want to actually use Faraday's law to solve for that induced current in the secondary loop as a function of properties of this system. So I've redrawn our picture here. Here's our primary wire. We'll have that carrying current I1 to the right. Here's our secondary wire, and I've identified some dimensions here. Width W, and we'll say the near edge of the secondary loop is the distance A away from the primary wire, and the far edge of the secondary loop is the distance B away from the primary wire. Let's take this in a series of steps. Step 1, use Ampere's law to get the magnetic field B1 produced by the primary. So primary wire here, grab onto it, thumb in the direction of that current, B field points in the direction of your curling fingers. So we know we're going to get a B field out of the page, up here, and into the page below. And let's utilize Ampere's law. Imagine an Amperian loop of radius little r surrounding that primary wire. State Ampere's law. That is the B field dotted with ds around this closed Amperian loop equals mu naught times the current penetrating through the open surface bounded by our closed Amperian loop. Okay, so we've solved this many times before. Let's say if our current is going this way, then our DS's will have pointing around this direction. So we'll be integrating in this direction around the loop, so that our the B field is parallel to DS's at all points on here. So this pink line I've drawn could well represent one of the looping B field lines around that wire. So we get B. This would be B1 here. B field produced by the primary times the circumference of that loop right there, 2 pi r equals mu naught, and the current enclosed is I1. So we recover the familiar result that the magnetic field produced by 1 as a function of distance from wire 1 and as a function of time has a magnitude given by mu naught times I1, which is a function of time, divided by 2 pi r. So there we have the magnetic field in this region depends both on your distance from the wire and depends on time, since I1 is varying with time. So it's a function of both r, little r, and t. Okay, so we've got our magnetic field everywhere out here. Step 2 now, we need to integrate to get the total magnetic flux through our secondary here. The magnetic flux through this rectangular surface bounded by our perimeter wire here. Magnetic flux as a function of time will come from the open surface integral of B1, which is a function of r and time, dotted with dA, little surface area vectors, everywhere throughout this rectangle. Okay, so we have to pick a direction for our dAs. Let's make the dAs point outwards so they're parallel to B1. So we'll have little patches of surface area, little dAs pointing out there. And if we have our dAs pointing out, we know that that also chooses for us the direction of dS's around here. So if my thumb is in the direction of dA, then my dS's will have to go counterclockwise around that rectangular loop. So let's have our dS's. I'll make those green. Our dS's pointing like this, counterclockwise around that loop. ds, ds. etc. Okay, so our dAs and dS's agree by right-hand rule. All right, so evaluating this here, B dot dA. Now, we've got an issue. The magnetic field in this example is not uniform throughout this region. The magnetic field is a function of distance r from the primary wire. So the magnetic field is strongest on this near side of the loop, but gets weaker as we go out here. So I can't simply pull B1 out of this integral. I can take care of the dot product. B1 and dAs point outwards in the same direction everywhere throughout this region. So I can write this would be the magnitude of B1 as a function of R and T times dA. So that takes care of the dot product. But B1 does depend on where we are inside this loop. So we have to decide how to carve up this loop into smaller pieces. I want to carve it up in such a way that each little piece has a single value for the magnetic field. So since the magnetic field depends on distance r, I would like pieces of our loop to have a unique value of r. So the plan will be to carve this up into thin strips like this. Each strip will be a specific distance, little r, away from the primary wire, and it'll have a thickness to it, infinitesimal thickness, dr. So that little strip of area right there will have a surface area vector dA pointing straight out. So this dA will represent the area of one of those thin little strips. So for some thin strip, dA equals, let's see, length times width. So the width is W, and the length here is W, and the width here is dr. So there's the area of one of these long, thin rectangles. So we're going to replace dA with that expression, and replace our B1 with this expression we got from Ampere's law. So this now becomes integral of mu naught I1, which is a function of time, over 2 pi little r, and dA is W times dr. And we have now our variable of integration, our independent variable, little r. And we see that we can perform this integral if we add up the contributions through every one of these strips, starting from the nearest strip going to the farthest strip. And we want to hit each strip once and only once, and not double count any strips and not miss any strips. So we can accomplish that if we take r from the smallest value of r equals little a here, to the biggest value of r equals little b. So our limits of integration will go from little a to little b. Now, let's pull out our constants. Let's see. So what are our constants here? What are the things that do not depend on the value of little r? Mu naught, 2 pi, W, none of those depend on our distance from the wire, but also I1 as a function of time. At some given time, I1 has the same value for every one of these strips here. I1 is just the current running through this wire. So note that what we're finding here is the flux through this loop at some one particular moment in time. So I1 at some particular moment in time is fixed for all values of little r. Little r is the variable. I1 is constant with respect to little r, since we're finding the flux at some particular moment in time. So we can treat that as a constant as well, pull it out, and we'll have mu naught I1, which is a function of time but not a function of little r. W comes out, the 2 pi comes out, and we're left with the integral of dr over r going from little a to little b, adding up the contributions through each one of those strips to get the total flux through our rectangle. Okay, we know our antiderivative here is natural log of r, and evaluate that from r goes from r equals a to r equals b. So we're about to have our answer here. Our flux through our rectangular loop as a function of time is equal to our collection of constants, the mu naught over 2 pi, the I1, which is a function of time, and then W, and the result of our integral will be the natural log of the ratio B over A. Okay, so we're not done yet. We haven't fully solved for the induced current in the secondary loop. We've got a few more steps to go, but this I think was probably the hardest one along the way, conceptualizing this integral to find this flux through an area where the magnetic field B varies throughout that area. We have a non-uniform B here, so we had to take care in setting up and solving this integral. Now we see that as the current varies with time, the flux will be varying with time. And we've got our geometric factors here, the W, the B, and the A kind of packaged together there, and just this constant out front. Next step will be to start applying Faraday's law.